So now we are proceeding to the factors affecting molar conductivity. I told you molar conductivity is different from electrolytic conductivity in one of our previous lessons, and we defined each of them. Now, this is lambda C. The other one was kappa. It was the symbol representing electrolytic conductivity. Some concepts will be borrowed and used here because they are a bit similar. And then we may not use others. So you remember molar conductivity is the conductivity of a solution containing 1 mole of electrolyte, a given volume of a solution, placed between 2 separate electrodes, each with unit cross-sectional area 1 meter squared, and separated by a distance of 1 meter apart. Which factors affect molar conductivity? Still temperature of solution. This affects electrolytic conductivity as well as molar conductivity. Second factor is magnitude of charge. Magnitude of charge on the ions. Third factor, we're going to see each of these factors separately. Third factor is ionic radius. Fourth factor is viscosity of the solvent. I would begin with this last factor, but I'm ending with it because we shall look at it elaborately. That is concentration of the solution. Concentration of the solution. That will be our last factor affecting molar conductivity. Let's look at the first one, which is temperature of the solution. So when I talk about temperature of the solution, we have the same effect. I don't want to repeat this. Same effect as for electrolytic conductivity. I think when I say this, you understand what I mean. What do I mean by this? It's what we have just seen in electrolytic conductivity. Whenever we have been having electrolytic conductivity, we shall replace it with the word molar. And the explanations are the same. What do I mean? Let's go back and recheck that point. We said that for a strong electrolyte, increase in temperature increases the kinetic energy of the conducting ions. Viscosity of water decreases. Ionic mobility increases, therefore increasing So we said increase in temperature increases the kinetic energy of the conducting ions. Viscosity of water decreases. ionic mobility increases. Therefore, increasing, we shall replace this with molar conductivity. That's for a strong electrolyte. For a weak electrolyte, the effect of temperature depends on the enthalpy change, which accompanies ionization. And the same effect as we have already seen. So what shall we say? For a weak electrolyte ionizes exothermically, increase in temperature decreases the molar conductivity. Decreases the molar conductivity. So we shall replace wherever we see electrolytic conductivity with the word molar. And explanation remains the same. So increase in temperature, decrease in molar conductivity because the degree of ionization decreases. Number of conducting ions per unit volume also decreases. Weak electrolyte ionizes endothermically, increase temperature, increases the molar conductivity. Because the degree of ionization increases, number of conducting ions per unit volume increases. So that's all about temperature. And I don't want to take a lot of time on that. Now, this brings me to a question. Which question says, distinguish between molar conductivity and electrolytic conductivity. That's part A. I know every one of you can do that. Second question says the molar conductivity of ethanoic acid molar conductivity of ethanoic acid solution containing 0.03 moles per liter is 8.50 units at 18 degrees Celsius and 14.7 units at 100 degrees Celsius. Explain this difference. So this is now application of knowledge because that's how questions may be set for you. When you look at the question, it's talking about molar conductivity. That's the first note I do have. The second case is that it's talking about ethanoic acid, which obviously is a weak electrolyte. The concentration is given. It's saying that this is the conductivity, molar conductivity at 18 degrees Celsius. And this is the molar conductivity at 100, meaning the temperature has been increased. And when the temperature is increased, even the molar conductivity is increased. That's what this shows. It shows that when the temperature was increased from 18 to 100, the molar conductivity was also increased from 18.5 to 14.7. What does that imply? It implies that ethanoic acid ionizes endothermically. And that's how you should explain that. So I expect you to approach that answer by saying that ethanoic acid is a weak electrolyte that ionizes endothermically. How have I known that it ionizes endothermically? Because the increase in temperature is increasing the molar conductivity. So I go on to explain and say, increase in temperature from 18.5 degrees Celsius to 100 degrees Celsius increases the molar conductivity. Because when we talk about this week electrolytes botanically, we talk about the number of conducting ions per unit volume increasing, and what causes it to increase? That's due to the increase in degree of dissociation. The degree of dissociation increases. Number of conducting ions per unit volume also increases. Don't talk about viscosity things and ionic mobility things here, because those ones are only talked of when we are talking of a strong electrolyte. So what's the treasure behind this? We are basing on this reaction to explain. Dissociation in water of ethanoic acid gives ethanoate ions and hydrogen ions. So according to Loch-Atelier, this reaction here is exothermic. I mean, it is endothermic, it's positive. Enthalpy change is positive. So when you increase the temperature, you're of course favoring the forward reaction, which occurs by absorption of heat. So the degree of dissociation of ethanoic acid increases to produce more conducting ethanoate ions and hydrogen ions, which increases the number of conducting ions per unit volume. That is the point behind that question. Now, we have looked at the effect of temperature. Our second factor is the magnitude of charge of the ions. That's the next factor. It is magnitude of charge on the ions. So we shall say increase, we shall say molar conductivity increases. Molar conductivity increases with increase in magnitude of charge. In magnitude of ionic charge. Why is that so? Ions with a charge of +2 are more conducting than ions with a charge of +1. In other words, the magnesium ion, for example, is more conducting than the sodium ion. Why is that so? These ions with higher charges are more strongly attracted towards the electrons, the oppositely charged electrons, and move faster. That's the reason. Okay. So you say ions with high charges or higher charges are more strongly attracted towards oppositely charged electrodes. faster. That's the point behind that. Let me give you an example of a question. Somebody can ask you to explain why magnesium chloride solution is more conducting than sodium chloride solution. So that's where the reasoning of ionic charge, magnitude of charge comes in. When you look at magnesium chloride, it is this compound here. And when you look at sodium chloride, it is that compound there. So the difference is in the cations, since the anions are the same. So I'd expect you to begin by saying that the magnesium ion in the magnesium chloride has a higher charge than the sodium ion in sodium chloride. Therefore, the magnesium ion is more strongly attracted towards the cathode than the sodium ion would be, and moves faster towards the electron, which increases the molar conductivity. So that explains why molar conductivity increases with the increase in magnitude of ionic charge. The next factor, according to our points here, we have looked at temperature, we have looked at magnitude of charge of the ions. We are looking at ionic radius now affecting molar conductivity. How does ionic radius affect molar conductivity? That's factor 3, ionic radius. It is surprising, very, very surprising. Actually, most people get confused with this factor here. Ions with higher ionic radius are more conducting in terms of molar conductivity than those with lower ionic radius. And hence, therefore, molar conductivity increases with increase in ionic radius. Why? Let's assume we have a sodium ion and the aluminium ion. Sodium ion, aluminium ion. You are aware that sodium ion has a larger ionic radius than the aluminium ion. Oh, I think we can better use ions in the same group. Let's use the lithium and sodium ion. That would be better. If I use the lithium ion and the sodium ion, the lithium ion will be less conducting in terms of molar conductivity, and the sodium ion will be more conducting, yet it's bigger. Why? The sodium ion has a larger ionic radius and a smaller charge density. Due to the higher ionic radius, to have a smaller charge density. The lithium ion has a smaller ionic radius and that gives it a higher charge density. So ions with a smaller charge density are less hydrated. They are not easily surrounded by water molecules. Whereas those with a higher charge density strongly attract the water molecules towards themselves if the high charge density and get heavily hydrated. So when an ion gets heavily hydrated, you find that that's the kind of ion. It is that beautiful girl who is always completely surrounded by boys everywhere at school. The sodium ion is that ugly boy or ugly girl who, when a few boys run after her, who are the boys here? The water molecules that are surrounding the ions. Now, when very many water molecules surround you because of your high charge density, your beauty that attracts them, you're going to be less mobile in a solution. This one, which has very few water molecules, will be more mobile in a solution because it has a larger ionic radius and a smaller charge density, less hydrated. So it will move faster and be more conducting in solution. So I've elaborately explained this because it disturbs most students. They always think that ions with a smaller ionic radius are always more conducting, which is not correct. So what shall we say? We shall say molar conductivity increases with increase in ionic radius. Why? The higher the ionic radius, the lower the charge density. And the less hydrated the ion. I think the point is very clear. The higher the ionic radius, the lower the charge density, or the lower the polarizing power, and the less hydrated the ion, or the less strongly attracted water molecules, or the less strongly surrounded by water molecules. Then you continue to say that the less hydrated ions move faster than heavily hydrated ions. And that implies that ions with a larger ionic radius are more conducting than those with a smaller ionic radius. That's all about that. What is our next factor? The next factor, I think it is factor 4, is which one? Is viscosity of the solvent. I told you if the electrolyte is to conduct, usually we put it in a suitable solvent. In most cases, which is water if it's soluble in water. So if I put sodium chloride in water as my solvent, the sodium chloride ion, the sodium ions and chloride ions will face a force of viscosity in water. That viscous force, okay, is being faced by the ions. And that implies that the higher the viscosity, then the lower the molar conductivity. Viscosity of the solvent. The point now we are looking at. So the higher the viscosity of the solvent, higher the viscosity of the solvent, the lower the ionic mobility. Hence, the lower the molar conductivity. The higher the viscosity of the solvent, the lower the ionic mobility. Hence, the lower the molar conductivity. You can take an instance or an example of oil. Let's assume you have a fish. Let's assume oil is a suitable medium for fish to swim in. It's not true, but let's take that assumption. If you put a fish, a live fish in water, this is water. And this is lubricating oil. If you have yoga fish in each of these, the fish will move faster in water and slower in oil. The reason is due to the viscous force or viscosity. The water exerts a less viscous force to the movement of the fish than oil, but the fish would still flow in oil or swim in oil. And that is always related to the density of the solvent itself. Density is related to the viscosity. So you are aware that oil is more denser than water. It's has a higher viscous force, the movement of the fish. Now our fish here are the conducting ions. So the higher the viscosity, the lower the ionic mobility, the mobility of the fish in the solvent, and the lower the molar conductivity. We have so far looked at 4 factors, and I wouldn't wish to look at the next factor, concentration, today. Let's look at the next factor, concentration, tomorrow, because it needs some more time and it involves graph plotting. After looking at that factor, then we shall draw some graphs or plot some graphs. After plotting some graphs, then we shall see some calculations involves what we call Corright's law. And then we shall have moved a good distance of the topic. Probably by within 1 or 2 weeks, we shall have to complete it. Thanks for attending this lesson. Have a nice time.